All right, so today we're not going to just memorize a bunch of reactions. Instead, we're opening up the chemist's toolkit. We're going to explore the different strategies, the different tools that chemists use to build one of the most important molecules out there, the carboxylic acid. So let's crack open that toolkit and get started.
So to kick things off, let's think about something you've probably experienced. What could possibly connect the sharp tang of vinegar in your salad dressing to, well, the painful sting of an ant? Sounds a little random, right? But the answer is pure chemistry.
And there you have it, that ant sting that's caused by formic acid, which gets its name from formica, the Latin word for ant. Makes sense, right? And that tang in vinegar, that's from acetic acid. Both of them are simple but pretty potent carboxylic acids. So what is a carboxylic acid really? What's the secret sauce? It's all about this one specific part, the carboxyl group. Think of it like a mashup of two other groups. You take a carbonyl group, that's the carbon double bonded to an oxygen, and you stick it right next to a hydroxyl group, the classic OH. That little combo, the COOH, is the heart of the molecule and gives it all its power.
Okay, let's grab our first tool from the kit. And this one's the sledgehammer, the oxidation pathway. This is what you pull out when you need some serious chemical muscle to get the job done.
You know, the whole idea here is pretty straightforward. You're going to overpower a molecule. You take your starting material, hit it with a really strong oxidizing agent, and that agent literally forces the molecule to become a carboxylic acid. It's super direct and super powerful.
So, where can we start? Well, one of the most common starting points is a primary alcohol. And all that means is that the alcohol's OH group is sitting right at the end of a carbon chain. These molecules are already halfway there, just waiting for that final push to be transformed.
And here we see it happen. You've got your primary alcohol, the CH₃COOH. What happens is that strong agent, like potassium permanganate, comes in and just rips away some hydrogens and shoves another oxygen in there. Boom! That end group is converted directly into the COOH of a carboxylic acid. It's a really clean one-step deal.
Okay, that's great for simple chains, but what if you're starting with something a bit more complicated? Like, say, an aromatic benzene ring that has a carbon chain hanging off of it. We call these alkyl benzenes, and they are another fantastic target for our oxidation sledgehammer. And this is where you really see the raw power of this method. It's kind of wild. Look at the top example, toluene, with just one carbon becomes benzoic acid. Okay, makes sense. But now look at the bottom one, with a longer chain. What do you get? The exact same thing. The oxidizing agent is so aggressive, it just chews up the whole side chain, and it doesn't care how long it is. All that's left is that single carboxyl group.
Okay, so we've seen the sledgehammer. Now let's pull out a more delicate tool, a precision instrument, if you will. This is the hydrolysis pathway, and you can remember it with a really simple phrase, just add water. So instead of using brute force to build something up, this strategy is all about gently taking a molecule apart. It uses water, sometimes with a bit of acid or base to speed things up, to snip a specific bond and reveal the carboxylic acid that was kind of hiding inside all along.
And you can see just how versatile this tool is. Check out this table. You've got acyl halides, acid anhydrides, esters, amides, a whole family of related compounds. And every single one of them can be turned into a carboxylic acid with this one simple method. It's this really cool, consistent pattern you see all over organic chemistry.
All right, let's zoom in on a couple of these, starting with the ones that have nitrogen in them, nitriles and amides. You can really think of this as a simple swap out. Whether you start with a nitrile or an amide, water comes in, breaks that bond to the nitrogen, and just slots an OH group right into its place. And just like that, you have your RCOOH product.
And hey, this same exact idea works for other starting materials too. Let's look at acyl halides and esters really quick.
So here's the big picture formula for how this works. RCOZ. Now, that Z is just a placeholder, right? It could be a chlorine or an ORG group, whatever. But it doesn't matter what C is. Hydrolysis comes along, picks that Z group to the curb, and puts an OH from a water molecule in its place. Super elegant, right? Okay, time for our third and final tool. And this one, well, this one's a game changer. The first two tools were about changing one molecule into another. This one, the Grignard reaction, is about actually building something new. We're doing construction now.
And that's really what sets the Grignard reaction apart. It physically adds a carbon atom to your molecule, making the chain 1 carbon longer. And get this, where do we get that new carbon atom? From something all around us. Carbon dioxide, the same stuff we breathe out.
So here's how it goes down in 2 steps. First, you take your super reactive Grignard reagent. Think of it as a carbon atom that's just itching to attack something, and you throw it at some carbon dioxide, usually in the form of dry ice. That locks the CO2 onto your molecule. Then, for step 2, and this should sound familiar, you just add a little acid and water to clean things up and release your final carboxylic acid. And this picture shows you exactly what you get at the end. The R group from your starting material ends up bonded to a brand new carboxyl group. So you start with an R group, and you end with R-COOH. You've literally built a bigger molecule 1 carbon at a time. How cool is that?
Whew! Okay, so we've seen a lot. Let's put our tools back on the bench and do a quick recap of the 3 main strategies we've just walked through. First up, we had the oxidation pathway. That's our chemical sledgehammer, right? For powering up alcohols and alkyl benzenes. Then we had the hydrolysis pathway, our precision tool. Just add water and you can convert all sorts of things. And finally, our construction set, the Grignard synthesis, for building new carbon chains using CO2.
You know, there's a line from our source material that just nails it. It reminds us that you can make these acids from so many different places. The goal is always the same: get that carboxyl group. The real trick, the art of being a chemist, is knowing which tool to pick for which job. And that really brings us to the big picture question, doesn't it? With so many powerful tools available, oxidation, hydrolysis, Grignard, how on earth does a chemist choose the right one? That decision, that's where being a chemist goes from following a recipe to being a true creator. And that's our explainer on the Chemist Toolkit.